Syllabus. Right. And so this class, so let me ask what the demographics are of this class. Who are environmental systems engineering majors? Vast majority. Who is not? Yes. And so Kenny, sorry, geosciences? Geoscience as well. Any other apart from chemistry? Earth science. So earth science, geoscience, chemistry, any others? No C's? And so that's great. That's a usual demographic, I suppose, in some respects. The class is an elective, I'll mention, in the environmental systems engineering, not a required class, which is maybe neither here nor there, but it certainly isn't a required class in that major. We've had a variety of different majors in this over the years: math majors, civil engineering majors, environmental resource management majors, etc. The class is a quote-unquote blended class, and most of the material of the class is served to you online, either through Canvas or through the kind of course web page for this. And so I just want today to talk about the kind of structure that we'll use for this. Let's see if I can get out of this. So most of the material, in fact almost all the material, is, if you know my name, I have to go down to this because I search on my own name too often. I'm sure you guys aren't that narcissistic. But if you need to find the course resource page, if you find my home page, and you find the course name, which is down here, Environmental Systems Engineering 408, it'll zoom you over to that. You can also get to that from Canvas. And so this course homepage is where most of the materials for this class are served to you, including the syllabus, which we just looked at, and all of the other course materials. So right now, I'm recording this class. I'm not recording you. I'm recording my voice and the screen. And ultimately, this stuff will go online on the course homepage, just like the first lecture of last year is recorded online. Okay, my merry band of friends. Such a chilly guy. Are we ready to go? Are we ready to go? I'm in the right mood. So the patois doesn't change from year to year. You probably can figure that out. But anyway, everything is supplied to you online. The syllabus is there, which we'll go through. The course notes are all available on there, 300 or so pages of them, which are kind of the overheads or slides that we'll use in the class, which you can download and use as you wish. There's another portion of an old web page which still exists, which isn't so useful anymore. All of the past lectures, classes, back to 2014, 2013, I guess, are available to you in the same way as we just looked at the previous ones. All screen captures and voice captures of what's going on. The assignments are served to you online, of which there are 9, except 8 doesn't exist, so there are actually 8 assignments. The prior tests are also served to you online, including, for instance, last year's. Not solved, but available to you online. And a review sheet for that midterm, which is in the week before spring break, and a rubric for the one other deliverable from the class, which is a presentation on remediation methods. So that's kind of a broad view of the things that are available. I know I've gone through that very quickly, so I'll spend a bit more time maybe talking about these individual components. So hopefully everyone can see this. We meet here, when we meet, 1:35 to 2:50. The online channel is on YouTube, but you can always get access to that through this course resources page, which we've just been on, which is identified there. There is a text, which is Contaminant Hydrology by Fetter. It was Fetter, but now it has some co-authors. I think he is now no longer with us on this planet. And so that's an optional book. I think of this class as being kind of an upper level undergraduate / graduate class in that transition. It's challenging in that regard, and I think that textbook fills that particular niche. We don't work from the textbook. There are no questions from the textbook. This is not for those of you who've taken my fluid mechanics class 303, it's not a prescriptive class like that with very precise questions to address where you get a single 9 points, 9 numbers after the decimal point solution to it. They're open-ended questions. So it's really a tools class, I think, for those of you who want to work in this particular area of groundwater hydrology, specifically on the transport, the occurrence and transport of contaminants and their remediation by different methods. And so I don't think you need the textbook, although there are copies of that, I think, in the Penn State bookstop. There are a few texts which are on reserve in the library. You'll see that maybe this second one here, Baer's book, a classic, Dynamics of Fluids and Porous Media, high-level, graduate-level textbook. Some of the notes are taken from that. And so if you find you can't follow me on some of the things we're talking about in the first part of the class, then that might be one resource to go and look for, and some other resources. So those are available in the EMS library on the second floor first floor of the Dyke building, right? And so those are available. My name is Derek Ellsworth. You know that. Call me by first name, last name, any other name as you desire. Zian is the TA for the class. There is a prerequisite. It's not a hard prerequisite, although Penn State are starting thinking about enforcing prerequisites so that people are prepared for classes. My view is the opposite. I've never enforced prerequisites. My personal view is that if you want to take a class and you feel that you're ready for it, all the materials here are online, and so you can review them beforehand to see that you're ready for it, then you should do it. If that endorsement, if you don't have the prerequisite, doesn't mean that I need to sit down for 4 hours a week with an individual to make sure that they can get through, but you take on a responsibility to do that. And so that's the deal, I think. And so if people have not got 452 and want to take this class, then I'll sign the, it never used to be required, but I'll sign the petition to be able to allow you to not have to switch it back a year or not avoid taking the class. In terms of the content, there are 8 assignments, assignments 1 to 9, missing number 8, which are worth 35%. Typically they're due at the end of the day on Thursdays. It's not quite as draconian as the fluids class, where there's an absolute deadline. They're usually done on paper and handed into the TA. They're often handed in class, and I take them to Zian. Usually my rule of thumb for a class like this is if you can get the stuff in before the person is grading it, then that's probably okay. Because that's really just the annoyance of it, right? You set a deadline so that you can actually grade it. So, but I'll let Zian set up her own requirements for that. There is a midterm exam. The midterm exam is on the Tuesday of the week before spring break. It is in class for only the class time, an hour and 15 minutes. And the material for the exam for the last few years has been verbatim questions from exams over the previous 5 years. And so those exams, as I showed you a little earlier, I guess we're still on the web page, aren't we? I showed you those exams earlier. And so last year's exam looks like this. It's all the same format. It's one question that talks about definitions. I want you to do a brain dump of everything you know about these individual features, which you will know about, hopefully, in 8 weeks' time. And then 2 kind of calculation questions that are identical. You'll see this question here given, I don't know, 5, 6, 10 years ago, whatever. And as you see also, and so you have a chance to be able to basically solve these questions on your own. I don't know if there are solutions floating around to them. I hope there aren't, but I can't help if that's the case. And then you have to regurgitate it in class. But it will be taken from those prior exams. As you can see, the class has been given for a few years. Yes, before you're born, right? If you're 21 or 22 now, for the majority of you, then so it's, and actually I think the first time is probably 96 rather than 97. Had different formats, had midterms and finals in previous incarnations, but that's not the case now. So there are 8 assignments. There's 1 midterm with 25%. There are content quizzes. I've changed it. No, it's still, I think there's 17 rather than 18, but they're all evaluated at the same weighting. And so the deal is you can come to class. There'll be a sign-up sheet at the end of class, not at the beginning of class, so you can leave immediately afterwards to show that you've been here. And if you do that and stay throughout, then you get 100% for the quiz later that day. If you choose not to come to class, then you do the stuff online, you view the stuff online, and you do the stuff online, and that's the same deal. And if you get 100%, great. If you get 50%, great. Yeah.
Are the classes typically the whole period length?
We do. Yeah, we usually go in full 75 minutes.
So the videos are the same length?
Yep. And so that's your option. So you can take it in 2 modalities. Some of the classes will be online only, and so this is kind of the syllabus in terms of weeks. You can see the 2, the red ones are the ones which will be online for everybody. You won't meet, and then you'll do the quizzes, typically 10 questions that are just talking about quizzing you on the material that's in that particular video. It's all accessible from Canvas. I guess the other thing, do I have to log in? Is Canvas on there? So if we go into Canvas, you're all very familiar with Canvas, of course. This is us, I believe. And assignments. I guess I can make it bigger, right? Probably should make it bigger. Assignments. Oh, let me go back to the home page. Student view. This is what you would see. Hopefully you'll see something. Assignments. So today is 1-1. No quiz today. But there's a quiz on 2-1. And so part of that quiz, well, actually you can't see it. I guess I could unlock it. So attached to this is a link to a video. This is just a very brief refresher before we start talking about the other things that we'll talk about in this class. I don't know why that's... Before we talk about the other things we'll talk about in this class. And perfectly cogent, right? And then a quiz. So this is just... So it's not quite live yet. I guess it will be live on Thursday. And so you see kind of questions. Blah, blah, blah. What does it stand for? Well, that's probably about right. I don't know what the other ones are, etc. And so you see 8 questions, so not 10, even easier. And so this, and so anyway. So that's the deal. I'm pretty sure you get 3 attempts. It tells you after each attempt what you got right and wrong. It doesn't tell you the answers, and so it's pretty straightforward. So the main thing, I guess, for you to know is that you have 3 attempts, and it takes the best of your 3 attempts. So of course you can game the system. You could have, if there are 5 multiple choice things in each one, you could have 5 people taking the quiz and all choose a different one, and yeah, I don't need to tell you how to do that. But yeah, so it's meant to. Well, I guess we do talk about academic integrity within the syllabus, so I guess that's fine too. All right, am I not getting back to where I am? Okay, so 408, so back where we were. So that's the deal with the quizzes, so that's the option. And so content quizzes are worth 15%. Remediation presentations, so there are 30 students, there are 6 topics of the presentations of different remediation methods. Biological methods, in situ biological methods, air injection, liquid injection, thermal treatment methods, electrolytic methods, etc., and site reconstruction, for another word, choice another word. So those are remediation presentations. Those, I'll make up the groups, so if we have 6 presentation topics and 30 students, then there'll be groups of about 5. Those presentations occur in the last few weeks of class in 6 individual periods. Last year, 2 years ago, we started giving the option to do it online as a YouTube video for the hour and 15 minutes of the class, which is really what it's supposed to be. We talked about the length of the class we spent together in the class, so it's about the same. That's the expectation. 2 years ago, maybe 1 or 2 groups did it online, and 4 did it in class, in person. Last year, one group, group 4, as you see here, did it online, in person, and the other 5 did it online. And so, as an incentive to those who do that, the deal is that you get 1% point for attendance at the presentations. Physical presentations, obviously, it's physical attendance. For the online presentations, I get you to supply a quiz that then gets posted with your recorded presentation. And so, if you look at the rubric for this, these are the 6 different topical areas. I'll make the groups. You don't get to choose your groups. It's based just on the idea that when you work for whoever, you have to work with the people that your boss or your bosses tell you have to work with. And so, so you have to deal with that issue. There is a peer review part which allows you to regulate your scores for people who have malperformed within your group, as sometimes happens. And this is just the material. So you talk about, it follows exactly the material that's in our notes. I want you to present the physical mechanisms by which the remediation method performs. What influences it? Does it work in low permeability, high permeability materials? What are the other controls? What are the field techniques that are used? Do you have to drill holes? If you do drill holes, how do you deal with those boreholes? How well is it used? Is it an industry standard? Is it in development? Is it a suggested method? What are the things that can go wrong and go well? And then the most difficult thing always is to find out how much does it cost per cubic yard or cubic meter of soil remediated in terms of ballparks. Afterwards, you do a peer review. And so since some people do it online, if you do it online, you need to provide 8 or 10 questions that can be posted on Canvas, just like the ones we saw, so that your classmates, when they look at the material online, they can identify that they've actually watched it just by using these quizzes, not by just clicking a button saying, yes, I did watch it, but actually something that forces you to actually watch it through the length and be able to understand it. The idea is, of course, that these presentations are a tutorial for your colleagues, and that they give you information that you'd like to have when you step out of here and start making the big bucks instead of paying your big bucks to Penn State for your education, right? I didn't want to do that. Okay. Oh my God! I'm trying to get it to, I'm trying to just reset this. So, what else do we need to talk about? Yeah, so that last one is remediation quizzes. You'll note if you add those numbers up, I don't think they come to 100. I think they come to 106 because of that last 6 points, and so that's my gift to you. I think the grading policy is the same as usual for me. 93.3 plus is an A, 90 is an A minus, etc. B's are all in the 80s, C's are all in the 70s, and D's, etc. And so that's the grading regime. Academic conduct, I guess we have here. You've heard it before, I won't tell you. Work together by all means, but submit your own work, which is the deal. Attendance is encouraged. Come to class. If you don't want to, that's not a negative. It's your choice. The deliverables are the assignments and the remediation example and the midterm, I guess, in terms of the graded components. And this is our schedule in terms of the Tuesday, Thursday classes that we do. So that's kind of it, I think. We haven't really talked about the material at all, but it's kind of I'm not sure it's necessarily a standard, but it is a contaminant hydrology class in terms of the spec. Who here has taken GSci 452? So large number of you. And so who taught it? Dave Yoxheimer? Do you remember who taught it?
John Hooker.
Yeah, John. Okay. Well, I was with his advisor in Ithaca, just PhD advisor, just 2 days ago. Yeah, okay. So John Hooker, okay, who I haven't met here yet. I know the name. So usually it's a class on physical hydrology. And so hydrology developed from the mid-1930s, I would say, onwards, looking at water supply. How much can you get out of the ground? How much can you pull out of the ground without depleting it irreversibly? What is the maximum rate that it is sustained by recharge that you can recover water from? And so around the 1970s, it became clear that that wasn't the only question. Not only should the resource be sustained in terms of the quantity of the resource, but also in terms of the quality of the resource. So contaminant hydrology grew up mainly from the 70s onwards with such tragic findings as Love Canal, where a bunch of corporations had bulldozed very nasty liquid substances into the subsurface, an old canal near Niagara Falls, New York, covered it up and built a bunch of houses on top of it, and all of a sudden people who lived there started getting sick. And so contaminant hydrology is really the science and technology of being able to understand how contaminants get into the subsurface, and therefore how you can avoid doing that in the first place, bless you. If they get transited into the subsurface, what they will look like, where they will go, and how they might spread naturally, how they might spread additionally by the things that humans do, pumping water, for instance, would spread them, and how you might actually remediate sites so that you can take those deleterious components out of the ground and away from the biosphere. And so the format of this class today is where we are now. We'll spend a little bit of time talking about physical hydrology, which is really the mechanisms by which fluids flow in the subsurface. And we're often interested in aquifers and how water flows in aquifers. But some of these contaminants that we have are typically immiscible fluids. They don't mix with the fluids. They might be solvents, dissolve other components, but they might not dissolve in water very quickly. So it's a bit like a petroleum reservoir. And so petroleum reservoirs typically have petroleum in them, and they might be quite highly saturated with petroleum, crude oil, but they might also have within them water. They typically have brines in them. And so when you pump petroleum reservoirs, you get both oil and water out of them. And so when these non-aqueous fluids go into the subsurface, then we have to worry about exactly how they move as a two-phase fluid. So our interest in physical hydrology is understanding two-phase flow of fluids that are denser than water, dense non-aqueous liquids, non-aqueous phase liquids, that will sink through the water column, just like they'd sink in a swimming pool, and fluids which are lighter, LNAPLs, light non-aqueous fluids, which would float on the surface of a swimming pool or float on the surface of the water table in the porous medium. And so understanding exactly how those get into the subsurface and then travel within the subsurface is the first part. And then understanding the rates at which they move, not as individual phases, not as pumping gasoline by moving the free phase gasoline out of the system, but by having it dissolve in water and then it diffusing in water, and then when you suck out the water of the system, you suck out not only water, but you suck out a portion of the invading fluid which is dissolved in that water. We'll talk about mechanisms by which they move and are retarded, not moving as quickly as they would do otherwise by things like sorption in the subsurface. We'll talk about mechanisms by which some of those substances become vapor because they typically have very low boiling points and they can volatilize. And one of the remediation methods, of course, is to heat the subsurface and allow them to vaporize and then gather them. What models we can apply to be able to represent their motion in the subsurface and therefore model things like infiltration and contamination and also the remediation process. And then after that, we will spend some time looking at how we define what the properties are of these aquifers and aquicludes. Aquicludes are the beds that keep aquifers apart and stop contamination from penetrating into the subsurface. What are the properties that we need to know for them? Permeabilities, storage coefficients, sorption characteristics. What are the things that we need to know to be able to define all of these processes that we'll have talked through in numbers 3, 4, 5, and 5, and that would be intrinsic in mathematical models in solving a system of equations that would allow us to solve those physical systems. And so the idea is that when you find a contaminated site, it's typically a field. It doesn't look any different from any other field. How do you figure out what's going on in the subsurface? And so we'll talk about methods of investigation, trenching and drilling to be able to get access to the subsurface and to take samples, methods of being able to understand what things like permeability are, either from those samples or by running in situ experiments, and a broad range. Very quickly we'll talk about geophysical characterization methods which use a proxy, such as looking at seismic wave speeds and linking that proxy to be able to say something about permeability. Link acoustic velocity to permeability and therefore profile for permeability in the subsurface without digging out the samples in the first place, and then being able to use that to make predictions about the rates at which these fluids can go through the subsurface. And the last part is for you, for remediation. And so we mentioned the rubric for what the presentation should be for remediation. That rubric follows the format, the structure, if you like, of one of the books which are in the list, Grubb and Sitar, which is, it's online, and so you can access it online to be able to look at that. You'll be able to, that's a resource that's available to you. I guess the other thing is that if you look in the course notes, it's a big file. It takes a bit of time to upload. If you look at the end of the course notes, if I can zip to the end, the last section deals with the remediation. They're not pretty, all of these notes. In fact, some of them, maybe none of them are pretty, but they actually have a decent amount of content included in them. And so in terms of remediation methods, the 6 methods are actually laid out in the it comes directly out of Grubb and Sitar, this EPA report that was a report responding to their project that they had. So it talks about the different methods, talks about what the processes are by which it works, talks about field implementation of it, it talks about some examples where it's been applied, what the limitations, what you need to be able to, whether you need high permeability or low permeability for it to be able to work, and costs and availability, etc. And so that stuff is available. So there's no mystery in this. I expect these presentations to go beyond that, but at least you have a starting point for material to be able to use to go towards that. So what else? Academic integrity. Those are the things that we have going on. And so we won't know about the online versus offline presentations until we get a bit further in class. But I'll set that up not too far. Once people have swapped in and swapped out of this class and so numbers are stable, then we'll put you in groups and then we'll set you up so you can actually meet and start thinking about your remediation assignments. Not done yet. Questions? Nothing? Everything's crystal clear? Yeah. That's a first for me. Crystal clear, that is. All right. Okay. Whoops, I didn't mean to do that. Okay, if that's the case, then I don't know what that is. Okay. Well, let's just, you've seen this. Do it. Does it not make it larger? It does make it larger. Well, so two things then, very quickly. So maybe we'll talk about some kind of big picture issues with some figures to look at the scope of what we'll do and to set the stage. And then maybe we'll talk about water in energy. And so if you'd have had 452 from Dave Yoxheimer, who works in the Marcellus Shale Center, then he would have no doubt talked about some of these things. But since you had John Hooker, I'm not sure what John would talk about. So State College, Penn State, the water you drink here is groundwater. It comes out of the ground by definition. The advantages of groundwater, of course, are that it's quite nicely protected from contamination by materials that can get very easily into surface water. So often surface water reservoirs, you can't go boating in them and you can't drive power boats because of gasoline going into the reservoir completely messes up the surface water reservoir as a potable water resource. But groundwater is free from that. 20 years ago, Bollesburg, where I lived, used to have surface water. They used to gather the water in the small stream that comes down that you see if you ever ski on Tussey Mountain or go up Tussey Mountain. They had deer pooping in the reservoir that collects that, which isn't good. And so they had a boil advisory, as I recall, for half a dozen weeks while they put together a tank. And so the standard way of doing it, I think the tank is still there, a big green tank, 30 feet high, 15 feet in diameter, where they can chlorinate it. And chlorine kills all these natural pathogens that result. And that was the solution before finally going to groundwater after that fact. And so groundwater is a valuable resource. My personal water supply is a well that's at our house rather than being on the system. But all the water that comes in this area now is groundwater. And so in terms of physical hydrology, a couple of local projects that might make sense. Anyone I did this last year, who's here from Pennsylvania? Do you have any Pennsylvanians? We have some. So anyone from around Huntington, an hour southwest of here? Where Boxer's Pub is and Juniata College are? No? And also, you see it on the bottle, Roaring Spring Water. One of their outputs from the town, one of their businesses, is Roaring Spring bottled water. And of course, when you buy bottled water, I don't know if you've done the math, but actually if you work out how much bottled water costs when you buy it, it's actually typically more expensive than gasoline by the same volumes. So it's a good business to be in since you get it basically for free. And so this was a case where New Enterprise Lime and Stone, they're an aggregate company who also make cement from the limestone that they dig up in a quarry at Roaring Spring. They wanted to deepen their quarry, and so they wanted to move this base down so it's lower than it was currently. And so Appleton Paper Company was and still is the largest business in town, and they use water for processing paper, turning trees ultimately into paper, and it's heavily water intensive. And so they were worried that since they absolutely relied on Roaring Spring, the name of the town being due to the fact that there is a spring that happens to access a big fracture zone, and that fracture zone is present on beds which have been folded tectonically. And so on this hinge at the top, you can imagine if you take a book and you bend it, it gets into tension and it would fracture if it was brittle. So this is a fracture zone that exists along the top of this ridge, and it takes water that flows from the east side flowing westwards. It gathers it in what is almost a groundwater dam on this side, where it's tight and there's low permeability. So it basically makes an underground lake that butts up against this dam. And then because the water can't get across this dam into the quarry, it goes down along this fracture zone and it comes out in the spring. And so Appleton's worry were that if you start going down an extra bench below where you are, all of a sudden you allow this high wall not to be held in place so strongly as it was before. It'll fracture, the fractures will open, the permeability will go up, and all of a sudden this won't be a groundwater dam, but the water will flow into the quarry. Not good for the quarry, but Appleton didn't care about that. What they did care about is the fact that if it goes into the quarry, then it's not going to be gathered by this groundwater dam, and it's not going to be sent downstream. And so I'm pretty sure that work I was doing in 1996, again before you were born. But I think that's still the solution that was arbitrated by DEP, Department of Environmental Protection, the regulator, if you like, was, well, let's take the quarry down one bench and then monitor it, see what happens. If nothing happens, then maybe we can go down another bench. And that's exactly the approach that they have. So that's just a geological map of that system. A second one, a kind of groundwater, but also energy related. Nivelle is a big lignite coal mine, surface coal mine in southeastern India, south of what was called Madras, what's now called Chennai, and is only about 50 or 100 meters below ground. Of course, you know, the biggest burners after, so China, I don't know if US is next and India next, but obviously India is powering itself by burning coal as a resource which it has. And to be able to recover that, at this particular area very close to the coast, the water table is quite high and the coal seam exists below the water table. And so if you want to be able to dig it out of the ground without wearing scuba gear, then you need to be able to somehow dewater it by pumping water around it. And so if you pump water out to be able to pull down the water table so that it's dry at the elevation that you want to be able to excavate the coal, then you have to do something with the water, and you have to worry about what the consequences of removing the water are. And there are a couple of consequences. One is that if you remove all that water, you have a huge source of potable water available to you that wasn't before in a very arid part of the world. And so as you drive from Madras or Chennai to Nivelle, you go from being very arid countryside to absolutely verdant green fields. And so it's used to spur agriculture, and it's great. So long as it's sustainable and you use it that way, that's great. The issue arises is that this mine, this isn't true vertical scale, it's much more gentle than that. But this mine is quite close to the sea, the Bay of Bengal. And the problem is that if you start pumping this water out of here at great rates, what you'll do is you'll get what's called saltwater incursion. Same problems that you have potentially in Florida if you pump groundwater. And that is the sea is all around you outside the strip of land. And so if you start sucking water out of these wells, you start a general flow of water towards, from the seaward side of this into the reservoir that you have, and potentially you suck water in, salt water, brines. And the problem with that is that it isn't necessarily the case that always your wells will be pumping fresh water. At some stage, if you pump in this saltwater wedge into here, at some stage you'll be pumping brines, and then you can't use them for irrigation, and then you can't either dispose of them. I guess you'd have to send them back into the sea, and it would be an unfortunate poor use of resources. So controlling water usage is a key issue. A third issue, untitled here, but that of being able to make nuclear power in the nuclear nations of the world, and then what to do once you have the waste from that process. So every developed country that has a nuclear power program has this issue with disposing of the radioactive wastes. The US is no different from that, although it isn't very far along in its own program. Most of these national programs to look at what to do with them have some strictures in place, regulations in place. In the US, they're created by the EPA, Environmental Protection Agency, and they're implemented by the Nuclear Regulatory Commission, NRC. And in a broad sense, the ideas for dealing with these wastes are geological isolation. So you put them in the ground somewhere, and you hope that that somewhere that they don't get out into the external biosphere. And so the typical conventional wisdom is maybe you bury them in tunnels or in repositories, which may be 300 meters to 500 meters below the ground surface. You arrange them far enough apart that the heat that's generated doesn't make this whole system very, very hot. And you hope that these materials are initially very low permeability and stay very low permeability, even with these thermal stresses that are added, so that if these canisters break, which they're designed for a certain percentage of them to fail, that if they break, then the material stays away from humanity. And so the typical idea, and I always use the analog of multiple redundancies, that why a plane has two wings instead of one is you want to be able to survive. It's perhaps not so funny in these days when such strange things are happening with aviation. But the idea is that you have, well, it's the reason that planes have two engines on them rather than one. If one engine goes out, you can typically land a plane on one engine. If you're going across the Pacific, you might want to have four engines, so if one goes out, you have 3/4 power instead of just half power. And the glide distances would be much longer, of course, if you're in the middle of nowhere. So some of the planes that go across the Pacific are four-engine planes. Much more expensive to maintain, of course, and to buy, right? Because you have to have four engines instead of two. And so the idea of multiple redundant barriers is that you have a waste package, which doesn't corrode very readily, which the glass waste is put into. And so the waste is vitrified, so the uranium byproducts are put in glass, which has a very low permeability and can't be leached out of. Those go into canisters, which are put in the ground. The canisters are put inside a steel container. Maybe it's a container that you use to truck them across the country on trucks or on railway carriages. And then you put them underground, and then you backfill it with another material that also has a couple of interesting characteristics. Maybe it's bentonite. So bentonite is a clay which is very soft, and so if it fractures, when it dries out, it can heal itself and seal itself. And also, it's a swelling clay. And so that if you get water coming into it, then it tends to swell, and if it swells, it makes a pressure that self-seals itself. It's the same things that are used in drilling muds, actually. And so you use that to be able to surround it. And then the geological barrier, of course, is that you're 500 or 300 meters below surface. And so that if the stuff leaches out of the glass and gets into the steel case and the steel outer case, or maybe a copper sheath, and then it gets through the bentonite and it gets out into the rock, then it still has 20 kilometers to go before it's carried downstream to somewhere where someone's going to be drinking it. And the very first assignment you'll do is for Yucca Mountain, which was going to be the nation's radioactive waste repository, to be able to look at those compliance type issues. And so it's kind of unusual in that the US is one of the few developed nuclear countries that doesn't have a firm plan put together of what to do. There was a plan to put it at Yucca Mountain in Nevada. After the election of President Obama in 2008, in January 2009, he convened a blue ribbon panel to look at Yucca Mountain. The panel said, nope, we can't put it there, but there's been no decision as to what to do in the absence of using that as a location. So we talked about a couple of groundwater supply problems, New Enterprise Stone and Lime, Novelli, nuclear waste programs around the world. The thing that we'll focus on largely in this class is much more mundane than that. It's kind of the bread and butter contaminant hydrology that you, as graduating students and graduating beginning engineers, would end up coming across. And we've alluded to this already when I talked about, oops, I don't know why I can't get to the top. It doesn't want to go to the top of this. And that is the role of things spilled from the surface into the subsurface. We talked about Love Canal, it's put in the ground. You know, the most obvious example in this area is Rutgers Nice, a Superfund site, which is towards the Nittany Mall, which has been sitting there all the 30 or so years that I've lived in levels now, and has been a Superfund site all that time. And I think what, in that particular case, they used to spray irrigate some of these solvents on the fields out there. Sounds stupid now. It was just done with a lack of thought, and it was conventional wisdom at the time. And that stuff exists now in the ground and is very persistent. And so standard contaminant hydrology, typically the largest polluters are these non-aqueous phase liquids. These non-aqueous phase liquids can be so-called L-NAPLs. I guess it's not labeled here. L as in lighter than water, in which case spills from underground storage tanks at gas stations where gas is lighter than water. The gas, if it spills, will sit on top of the water table, maybe depressing it slightly because there's a column of fluid above it, which is higher than the air which exists elsewhere. And of course, it wouldn't be a problem if it stayed there and it wasn't soluble in water, but typically it is soluble in water. So it will dissolve along the interface with the water in the pore space, and it'll be carried downstream to drinking water. And the D-NAPLs, D is for dense, non-aqueous phase liquid, denser than water. And the idea is that no different from dropping something that's denser than water into a swimming pool, it goes directly to the floor of the swimming pool, the bottom of the swimming pool. If it's got to go through a porous medium that happens to have a water table in it, it's exactly the same process with some other components added, but it will sink through the water table and it will only stop where it hits something that it can't get through, a so-called capillary barrier, which would be the swimming pool bottom in the case of the swimming pool, or it would be a very low permeability, very low porosity clay or shale layer in the case of these components. So most of the stuff that we'll do in this class is talking about the transport of non-aqueous liquids in the subsurface, to be able to describe exactly what these distributions look like in the first place. Does it look like a nice saucer? What is the form of this? Is this going to be full of non-aqueous phase liquids? No. And if that's the case, then what do they look like in this? Once we know what the distribution of non-aqueous phase liquids in this are, how do we understand how it would transport and dissolve in the water that's flowing through this? And how far will it go downstream? In what concentrations will it go downstream? Would be questions that we'd like to ask. And finally, how do we get it out of there? What are the mechanisms that we can use to pull it out? If we suck the water out, does it include the stuff that's dissolved in the water itself? Clearly it will be. If we suck out hard enough, will it pull out the non-aqueous fluids? Almost certainly not. And so we need another solution to be able to do that. And so those are the kinds of questions that we'll attempt to answer in this class. I'm not sure what else I have in here. The one other thing, let's just spend 2 minutes on this. Yeah, I'm not going to go through this. The things that we'll talk about in this class are generically in talking about the movement of fluids in the subsurface. Certainly in the news now, and in the news now for 20 years, but now much more than ever before, Greta Thunberg and all the climate change stuff, Australia on fire right now, and all the other things. Energy and the ways to create energy in a sustainable way is a big issue. And so a number of people have commented on that. Richard Smalley, the Nobel laureate who discovered buckyball carbon-60, and Holden, who used to be Obama's science advisor, recognized that. But many of the big-scale energy schemes involve the subsurface, and almost all of them involve fluids in the subsurface. Not things that we'll address in this class per se, but peripherally, flow in porous and fractured media are exactly what we do in this class. So one possibility is to be able to harness the heat from the subsurface. Certainly done on the west coast of the US, Geysers geothermal field, 100 kilometers out of San Francisco, gigawatt, the biggest, I think it's the biggest geothermal field in the world, is one that sits on a plate boundary, San Andreas Fault basically, where lots of things are moving on the plate boundary. It's straining, and so porosity keeps on getting opened up, and so there are open flow pathways in there. The challenge in this, of course, is being able to get the power not in these very select locations on plate boundaries, but here, underneath Penn State, in the middle of the continental US or on the East Coast where the demand is. And so I just came back from a workshop at Cornell. Cornell planned to drill a 5-kilometer hole on campus. They plan, like Penn State, to be carbon neutral by 2035. And their first step to do that was to take coal off campus and replace it with gas, as Penn State did. Much lower carbon per unit energy. And the second phase now is to be able to replace that gas by deep geothermal heat for heating, not for electricity, and for also burning chicken poop, I think, biomass that they develop from their agricultural industries that are around them. And so one of the schemes to do this is so-called EGS, Enhanced Geothermal Systems. Drill a well, stimulate it, you frack it, don't say that too loud, to be able to generate some permeability. You drill another well to be able to intersect that new permeability, and you pump down cold water, just like a radiator in a car, picks up the heat from the subsurface, and then comes up hot. You use it, whatever use, electricity or direct use, and then you pump down cold water. Clearly, fluid flow in porous and fractured media, just like we're talking about. Nuclear waste disposal. This is kind of the schematic of Yucca Mountain, which is shelved now. For the basic idea, they have a tunnel in there that goes into this repository at 300 meters depth. You'd excavate all of these parallel tunnels, which are these, and then you'd put these waste canisters in it. These would be railroad cars, which would be driven in, so they're the size of railroad cars. You know, these black oil containers you see, Procore oil containers you see driving on the rails these days, about that size. And then you fill this up with backfill, maybe or maybe not, and then you walk away. You put a marker on it, you monitor it for 50 or 100 years, you put a marker on it so that people, if they come there in 2 million years or so, know exactly what it is, just like you do on a spaceship, and you hope that no one goes back and digs it up. Burning fossil fuels, either coal with high carbon or gases with lower carbon. One solution is to dump the carbon, capture the carbon and put it on the ground. Again, has to be there for centuries, safely interred. And so the mechanisms to do that are either to use existing petroleum reservoirs which are depleted and have lots of space in them, put into saline aquifers of which there's lots of capacity underneath the US and other developed countries. Put it in coal seams and take out the methane. Of course, you get more carbon if you take the methane out. And the mechanics of doing that are exactly the same as groundwater hydrology and contaminant hydrology. CO2 goes in as a fluid, a liquid, under pressure. It goes in under an aquiclude or a cap rock, so it doesn't get out. And you want all the potable water sources that you have to be separate from it so they don't become acidified by the CO2, which will make carbonic acid out of them. And of course, particular to Pennsylvania, is now the issue of natural gas. So it's been a huge boost to Pennsylvania economy. You could argue that it's also a big boost in terms of moving to a lower carbon energy economy, because it's typically cheaper now than burning coal, so it naturally replaces coal, and it's also lower carbon, cleaner per given amount of energy that it gives up than coal. And so maybe half the carbon is involved in it. And so it's been brought about by horizontal drilling. So the technologies that have driven it are being able to drill horizontally maybe 1 kilometer or 1.5 kilometers once you're down at 3 kilometers in depth. So you kick off at this bottom place and you drill maybe 1.5 kilometers along here. And massive hydraulic fracturing, which is of course is controversial, but it's the mechanism by which you unlock the gas resource that's been in place for many millions of years. And so the issues are, one, if you do this massive hydraulic fracturing, what does that do to the water that's present in the aquifers that you're using as potable water supply? Is it a problem? Which is one of the main problems. And of course, in doing that, there are a variety of studies that look at that. The geometry works in your favor in the fact that if you're in the Marcellus, probably you're fracturing down at 3 kilometers or 9,000 feet, and the potable water is in the top 500 meters, 500 feet or so. And so you're a long way away from that water, but some studies have definitely found dissolved quantities of methane in water, and typically that methane concentration is measured as you go away horizontally. This lower axis here is distance away from a gas well, and these individual data points are from water wells, which are that distance away from this main gas well. And it seems to be that the major concentrations are not where it's been fractured away from the well, which might go out kilometers or multiple kilometers away from the well, but actually it's some kind of leakage that's probably coming from somewhere within the well, because it's not been particularly well made in the top. And so there are many aspects, I guess, of energy production that involve the same kinds of things that we talked about in this class. But as I say, our focus almost exclusively, this is an aside to give you some kind of view of the breadth of the kinds of things that we're talking about. All of the things we're talking about in terms of fluid flow and fluid transport in porous and fractured medias bear heavily on these last things we talked about, but we'll look at it almost exclusively in relationship to the most difficult problem that we can imagine, and that is the transport of non-aqueous phase liquids in the subsurface, such as L-naples and D-naples, and that's what we'll start talking about on Thursday, this Thursday. Any questions before we kick off? No? You're very easy. It's always good to have actually a protagonist, someone who wants to give a bit of banter. So if one of you feels courageous and wants to do that, it makes the class go much easier. Yeah. Go in your eyes and your head. Yeah. So it can be a conversation.